Hey, hello ib1 students. Welcome after this Easter break. As I wrote in Google Classroom, the major test in physics will be next week in 8 days. You have more details in Google Classroom as a post. Okay, so let's write next lesson of revision to test. Okay, still I'm talking of course about thermal physics. And today I'm going to do first give you material which is obligatory for the test from the beginning to the end, something we did during these meetings. Second, I'm going to solve with you exercises, multiple choice questions from Tsokos. Okay, and finally, I'm going to attach, because this is something I forgot to do last time, to attach one page of exercises, not from Tsokos, from different source. The activity is per 39 points, so for 58, let's say 60 minutes. It will be your task to do during our lesson or as a homework. I will be talking about these exercises tomorrow, Thursday, during our next meeting. So last meeting before your major test in thermal physics. So again, first revision, next let's do with me Tsokos exercises, and last, finally, activity for 58 minutes. Please do this for tomorrow, so today or today during our class or as a homework, because I will be talking about these exercises at Thursday during our last lesson before major test. Is it clear? Okay, so I hope that you are prepared to the lesson. You have pen, pencil, your notebook, Tsokos calculator, and eventually ruler. Yeah, so let's start with the revision. What should you know on the test, on the major test in thermal physics? Of course, I'm going to give you two parts, MC questions and open questions, but of course probably in the form of one test of weight of 4. So not two separated tests, multiple choice questions weight of 2 and open questions weight of 3. It will be one test and the grade will be of weight of 4. Yeah. Okay, second, time will be strictly limited to, let's say, 60 or 80 minutes, depends on the length of the test. I will upload the test at the exact time, and your task will be to solve it at the exact time. Of course, I give you half an hour extra time to make a photo or make a scan and attach in the form of one PDF file, but detailed instructions will be given later, just before the test. So time will be limited only to the time of test. Is it clear? Okay, so at the beginning we were talking about heat or thermal energy. Okay, we're talking about internal energy. Okay, and about temperature. Okay, so in the case of internal energy, you have to know that this is the sum of kinetic energies of all molecules related with motion of the molecules and potential energies of all molecules related with fact that molecules interact. Okay, what is the temperature? Temperature is the measure of average kinetic energy of the particles in the substance, and here we have to know how to link temperature with the average kinetic energy. Okay, about this, you have to know how to derive this expression. In the case of thermal energy, you have to know that this is the part of internal energy which can flow from one object to another as a result of temperature difference. And here you must know a lot of details with specific heat capacity, which is amount of thermal energy which is needed to heat up 1 kilogram of substance by 1 Kelvin. So this is when substance can change temperature, and specific latent heat, which is related with energy needed to change the phase of 1 kilogram of substance at constant temperature. Okay, and in both cases you have to know two methods of measuring. Yes, so electrical method and method of mixtures. We did this during our lessons. Okay, so this is first part of thermal physics. Second part of thermal physics was related or is related with an ideal gas. Okay, we were talking about three laws: Charles law, Boyle's law, and pressure law, and about the graphs. And conclusion was equation that PV over T is constant, and this constant depends on the number of moles and another constant called gas constant. Of course, P is a pressure, V is a volume, T is temperature in kelvins, and N is number of moles. Of course, you have to know definition of 1 mole. So 1 mole is related with amount of substance which contains exactly the same number of molecules as 12 grams of carbon 12. Okay, so it refers to the carbon 12. Remember about this. And this number of molecules is called Avogadro constant. So you have to know also what is the Avogadro constant. It's 6.02 times 10 to the power of 23. And this is the number. You have to know also what is a molar gas, a molar mass. Okay, molar mass is mass of 1 mole of the substance. And what is the link with molar mass, number of moles, and the number of molecules, and Avogadro constants, etc., etc. Okay. In this case, in the case of Clapeyron's equation, PV equals nRT, you have to know that for constant V, P is proportional to T. For constant P, V is proportional to T. For constant V, P is proportional to T. And for constant T, P is inversely proportional to V. Okay, and you have to know a molecular model of an ideal gas. A molecular model of an ideal gas says that molecules are very, very small compared with distance between molecules, and that molecules move randomly. Molecules do not interact except collisions. Collisions are perfectly elastic, so no time is spent in the collisions. So what does it mean? It means that internal energy of an ideal gas is related only with temperature, so only with average kinetic energy of the particles, because ideal gas has no potential energy because molecules do not interact except collisions. Another very, very important fact is that the volume of the gas at 0 kelvins is equal to 0, so gas cannot be liquefied. Okay, and of course you have to know a few words about absolute scale, about Kelvin scale, that if temperature is the measure of average kinetic energy of the particles in the substance, then there must be minimum possible temperature, called absolute zero, at which molecules do not move, and this temperature, the equivalent in Celsius degrees scale, is minus 273. Okay, so this is all you have to know in the case of theory. Remember about definitions of specific latent heat and specific heat capacity, and of course additional equation which is very, very useful here. Power is work over time, because when let's say heat is delivered by a device, electrical device of known power, then you can calculate amount of heat which is delivered as a product of P and T. Okay, so this is our first part of today's lesson, so revision to test. Please know this, please learn this. If you need stop video, note these sentences, write these words or descriptions, and when you will be ready, turn video back, and I'm going to talk about multiple choice questions from your favorite book. Okay, okay, and you're ready. So open your Tsakos on page number 140. 2, and I'm going to solve questions from 1 to 10. I hope that you solved these questions previously, so now you can check if you didn't do this. So please solve one question, stop video, solve first question, turn it back, listen to me, stop it, solve the second, etc., etc. Okay, I'm going to solve all 10 questions, and when you did this previously, let's check your answers. Okay, so new slide, multiple choice questions. Okay, so 1 by 1, exercise number 1. I'm going to copy 1 by 1 and solve here. Okay, first, body X whose temperature is 0 is brought into thermal contact with body Y of the same mass but higher temperature. The only exchanges of heat that take place between X between X and Y, and specific heat capacity of X is greater than specific heat capacity of Y. Which statement about the final equilibrium temperature of the two bodies is correct? Of course, you have to start with law of conservation of energy, which says that heat, which is thermal energy which is taken by X, must be the same as thermal energy which is lost by 1. It's written here. The only exchanges of heat that take place between X and Y are between X and Y. So what is X? Both objects change temperature. There is nothing about change of phase. Okay, so we can write that specific heat capacity of X times mass of X times change of temperature of X must be exactly the same as specific heat capacity of Y, mass of Y times delta T, change of temperature of Y, and it's written equal mass. So mass X is the same as mass of Y, and it's written specific heat capacity of X is greater than of Y. So we can write that Cx is greater than Cy. So to be equal, then delta Tx must be less than delta Ty. What does it mean? It means that X changes temperature less than Y. So if X has 0 and Y has 100 and X changes less than Y, the possible is less than 50. So finally, the temperature of the two bodies, the final equilibrium temperature, will be more than 0 but less than 50, so answer B. In exercise number 1, the correct answer is B. Oh, okay, yeah. So at thermal equilibrium, both will have the same temperature less than 50 because change of temperature of X will be less than change of temperature of Y. Okay. Now, as I said, you can check or you can stop video. I'm going to solve exercise number 2. So if you didn't do exercise number 2, please stop video and do exercise number 2. When you will be ready, turn it back. Okay, exercise number 2, red color. Energy is provided to liquid at its boiling point at the rate of p joules per second, and the rate at which mass is boiling away is mu kilograms per second. Specific latent heat of vaporization of the liquid is. Okay, so the question is about specific latent heat of vaporization, which says that this is thermal energy which is needed to convert to boil a particular mass of the liquid. We don't know Q, but we know power. Power is Q over time, so Q can be written as power times time. And again, we don't know M, but we know rate. So what is a rate? Rate is mass over time, so mass can be written as rate times time. So finally, we have latent heat given by P over mu, which is B. So exercise number 2, the correct answer is B. Okay. Stop video, copy this, and you will be ready. Turn it back. Exercise number 3. Okay, exercise number 3 is here. Okay. The following are all assumptions of the kinetic theory of gases except which one? Okay, so the question is about kinetic theory of gas. Okay, so let's check. The duration of the collision is very small compared to the time between collisions. This is true, and this is part of kinetic theory of gas like ideal gas. Okay, so A is true. Okay, B, the collisions are elastic. It's also true. Okay, collisions must be elastic, like a model of an ideal gas. C, the average kinetic energy of molecules is proportional to the temperature. This statement is true because in general the average kinetic energy of the molecules is proportional to the temperature in Kelvin scale, but this is not the part of the kinetic theory of gas. Like in ideal gas, molecular model of an ideal gas, this statement is not a part of a molecular model. Let's check D. The volume of molecules is negligible compared to the volume of the gas. Okay, this is true, this is part of kinetic theory, so there is only one which is not true, C. So answer for exercise number 3 is C. Okay, so for exercise number 3, answer is C. Okay, exercise number 4. So here, 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 and new slide, paste it. Okay, in the context of a fixed mass of an ideal gas, the graph could represent the variation of. Okay, fixed mass of an ideal gas, so PV over T is constant. Yes, so at constant P, V is proportional to T. I'm talking about this, I'm not talking about A, B, C, D yet. Okay, remember that it crosses 0, so if x-axis represents temperature, the temperature must be expressed in kelvins, because the minimum possible temperature is 0. Okay, in Celsius degrees we have less temperatures than 0. So in my opinion we can cross B and C, because in both in B and C we have Celsius scale, which is probably not true. Okay, so let's check A and D. In A, pressure with constant volume at constant pressure with volume at constant temperature. So let's look. If temperature is constant, then PV must be constant, which is not true because P is proportional to 1 over V. So A is not true, so probably D. Let's check. Pressure with inverse volume at constant temperature. So we have pressure proportional to inverse volume at constant pressure, so correct answer for 4 is D. Okay, so at constant temperature, pressure is proportional to inverse volume. Okay, exercise number 5. The temperature, okay, let me paste this here. Okay, and blue color. The temperature of an ideal gas of a pressure 200 kilopascals is increased from 27 to 54 degrees Celsius at constant volume, which is the best estimate for the new pressure of the gas. It's quite easy because let's look again. PV over T is constant, and it's written that the volume is constant. If volume is constant, then pressure is proportional to the temperature, okay? Or change of pressure is proportional to change of the temperature. What is the change of temperature? Temperature changes from 27 to 54, so it increases. So final pressure must be or A or B, because only A and B are bigger. So we can cross C and D. And let's look. A says that pressure increases twice. Does temperature increase twice? Of course not, because temperature must be expressed in kelvins. So in this example, temperature rises from 300 kelvins to 327 kelvins, so by almost 10%. So if temperature rises by almost 10%, then pressure must also rise by almost 10%. So there is only one correct answer, 220 kilopascals. Of course, you can calculate numerically, but it's not necessary, okay? Temperature doesn't increase twice, so pressure cannot increase twice in this example. Okay, exercise number 6. Okay. A container of an ideal gas that is isolated from its surroundings is divided into two parts. One part has double volume, maybe here. One part has a double volume than the other, and the pressure in each part is P, and temperature is the same. So here is P, here is P. Okay, so the partition is removed, and the question is about new pressure in the container. You don't need to use Clapeyron's equation, PV equals nRT. We did something similar, but in this case it's easy. Let's look. If temperature is the same and pressure is the same, then what happens if partition is removed? Pressure must be the same. We have the same pressure on left and right side, so the existence of partition is not important. Pressure will be the same, so correct answer is A. Exercise number 7. Different quantities of two ideal gases X and Y are kept in the same temperature. Which of the following is a correct comparison of the average kinetic energy and internal energy of the two gases? Okay, these two gases have the same temperature. What does it mean? The same temperature means that both have the same average kinetic energy, so it can be A or B. Okay? And now what with the internal energy? Okay, internal energy depends on the average kinetic. Internal energy depends on the kinetic energy. Internal energy is the sum of kinetic and potential energies of all molecules. Of course, this is ideal gas, so ideal gas has no potential energy, but we have different quantities. What is important in this question? Important is in this question is word average. Average kinetic energy, if temperature is the same, is exactly the same, but internal energy is not average. Internal energy depends on the amount, it's the sum of all. So if we have more gas of the same average kinetic energy, then all molecules together have more total kinetic energy, so bigger internal energy. So if quantities of gas are not the same, then internal energy at the same temperature will be not the same. So correct answer for exercise number 7 is B. Average kinetic energy is the same because temperature is the same, and the internal energy is not the same because we have the same average kinetic energy, but amount of molecules is different, and internal energy depends on the amount of molecules, so it's not the same. Exercise number 8. Okay, the temperature of an ideal gas is doubled, the average speed of the molecules increases by a factor, blah blah blah. Okay, so we have to link temperature with average kinetic energy. You know that temperature is proportional to the average kinetic energy, which is proportional to squared speed. Okay, so let's look. If temperature is 2 times bigger, then what must be speed? The right hand of this equation must be also 2 times bigger. So speed must be increased by a factor of root of 2, because the root of 2v squared gives 2v squared. So correct answer is A. Speed increases by a factor of root of 2. Okay? Again, temperature is proportional to squared speed. If temperature is doubled, then squared speed must be doubled, so speed must be multiplied by the root of 2. Okay, exercise number 9. Two ideal gas, or let me copy, paste, and maybe a new slide. Okay, two ideal gases X and Y are kept at the same temperature. Gas X has a molar mass mx and gas Y has a molar mass of my. The ratio of the average speeds of the molecules of gas X to that of gas Y is. So what is important? Temperatures are the same, which means that average kinetic energies are the same. Okay, we can cross half, and we know that one gas has different mass than other, and the question is about average speed of X to average speed of Y. So let's look. We can write Fx Vx squared over Vy squared is the same as mass of Y over mass of X, or other words, Vx over Vy is the same as the root of mass of Y over mass of X. But here in this equation, m represents mass, real mass of the molecule. But here we have to refer to the molar mass. But let's look. What is the important here? If molar, the mass, the amount is not specified, so this question is not complete. This question is not correct. We can assume that if we have the same amount of mass of gas X and gas Y, let's say 1 mole, then mass of the same quantity is proportional to the molar mass. Let's imagine that molar mass of X is let's say 2 and molar mass of Y is let's say 3, and we have the same amount. Then real mass of X is proportional to 2 when the real mass of Y is proportional to 3. So assuming that we have the same amount, equal moles of gas of X and Y, the answer is that ratio between speed X to speed Y is the same as the root of mass Y over mass X. So I assume that this is the correct answer is D, and my assumption is that we have the same amount of moles of X and Y. Okay? In other case, this exercise is unsolvable. Okay, and exercise number 10, the last one here. Let me copy, paste, and talk. Okay, the pressure of fixed quantity of an ideal gas is doubled. The average speed of the molecules is also doubled. The original density is P. What is the new density? Okay, in general, what is density? Density is mass over volume. Nothing happens with mass of this gas, but something happens with volume. We have to check what happens with volume. We know that the pressure now is doubled, and speed is also doubled. If speed is doubled, then temperature is 4 times bigger. We know also PV equals nRT, and we are looking for V. So it can be written that V is nRT over P. The same amount of gas, the same constant, and temperature is 4 times bigger, pressure is 2 times bigger, so volume increases by factor of 2. Okay, so mass is the same, volume is 2 times bigger, so we have half of previous density. So density is half of the original one, so correct answer is A. Okay, nice exercise. The last one is nice exercise. Density is mass over volume. Mass doesn't change. What happens with volume? By using pressure, new pressure, temperature, new temperature, we can estimate or calculate new volume, which is 2 times bigger. So if we have the same mass and 2 times bigger volume, then density must be 2 times less, must be divided by 2. So correct answer is A. Okay, so we finished another part of today's lesson, multiple choice questions. So we did revision, multiple choice questions, and third part is will be done by you. In the attachment you have one PDF file containing few exercises. Overall number of points is around 40. Okay, so you have to spend with this around 60 minutes. Okay, if you have a time, then please start it now. If not, it will be unfortunately your homework, or otherwise try to do this the best. Tomorrow, so at Thursday, I will be solving these exercises, so you will be checking your solutions and your methods with mine and eventually comparing results. Okay? So remember, test is in 7 days. Tomorrow I will be solving exercises I've attached today in this PDF file, and in 7 days you have major test in thermal physics. Okay, if you have any suggestions, any questions, write this as a comment in the form of post, not in YouTube, in the Google Classroom as a post. If you have any questions about solutions, ask me in the same form. Okay, thank you for watching. Good luck, stay at home, and see you. Bye.